We've already learned that light can be bent from its ordinary straight line path by reflection and by refraction. Now we learn another way in which light bends. Any bending of light by means other than reflection and refraction is called diffraction. Diffraction is the bending of light as it passes the edge of an object, creating a fuzzy edge. It also occurs when a wave passes through an aperture. Diffraction occurs for water waves also. Here we see a physiker at a water tank with a partial barrier. She oscillates a meter stick up and down and creates plane waves on the water surface. Water oscillating at the opening acts as a source of waves, which fan out from the opening. We say the waves diffract through the opening. Here's top view photos of water diffracting through openings of various sizes. What do these three photos show? They show that the smaller the opening relative to the wavelength, the greater the bending of waves at the edges of the opening. In other words, the smaller the opening, the greater the diffraction. And here's a top view of waves encountering different objects in their paths. In A, we see how the waves spread into the shadow region. In B, where the object is about the same size as the wavelength of waves, we see the shadow is soon filled in. In C, for the same size object, we see minimum diffraction for wavelengths that are short relative to the size of the object. A sharper shadow is cast. Apply this to viewing very small objects with a microscope. For objects about as small as the wavelength of light, diffraction blurs the image. If the object is smaller than the wavelength of illuminating light, any image is lost to diffraction. Objects are best seen for relatively short wavelengths of illuminating light. Less diffraction occurs when the wavelength is small compared with the object being viewed. Let's look at light passing through an opening. When the opening is large compared with the wavelength of light, a sharp shadow is cast. Only a bit of fuzziness at the edges. If light is passed through a thin razor-sized slit in a piece of opaque cardboard, the light noticeably diffracts. The sharp boundary between the light and dark areas disappears and the light spreads out like a fan without sharp edges. Diffraction is evident. Light diffracting through a single slit is one thing. Light diffracting through hundreds of closely spaced slits is another. Such an array of slits makes up a diffraction grating. Here's Jill Johnson of City College of San Francisco with an oversized diffraction grating used for classroom demonstrations. Different frequencies of light diffract differently, and a diffraction grating separates light into its many frequency components. Jill compares the light diffracted from helium gas at the left with mercury gas at the right. We see that each element, when made to glow, emits its own pattern of vertical colored lines. Just as a prism separates light into its component colors by refraction, a diffraction grating does the same by diffraction. Yum to both prisms and diffraction gratings. Not only thin slits, but thin ridges produce diffraction of light. Hence the yum colors you see on a CD, which are produced by diffraction. And we see diffraction beautifully apparent in the feathers of peacocks, and in the feathers of many birds. When feathers ruffle and colors change, aha, you're witnessing diffraction. Again, any bending of light not due to reflection or refraction is due to diffraction.
Let's talk about single slit interference. Now, if I were you, I'd already be upset and a little mad. Single slit interference. Wave interference, is by definition multiple waves overlapping at a single point. So how could a single slit ever produce multiple waves that could overlap? I mean, when we had a double slit, if I put a barrier in here and we have a double slit, at least then, okay, I send in my wave, it gets over to here. There's a small hole. We know what waves do at a small hole. They diffract, which is to say they spread out. At least with a double slit, you would have two waves spreading out. Now they can overlap. Interference. But for a single slit, how are we ever going to get this? Well, I never really told you why do the waves spread out at a hole? Why does diffraction happen at all? Why, when waves encounter a hole, do they spread out? And the answer to this question is the key to single slit interference. And the answer to why they spread out at a hole is something called Huygens principle. And I can't say it. This is a Dutch physicist, scientist who figured this out. Huygens principle. And I apologize right now to all the Dutch people out there. I'm butchering this name. Huygens principle, easier to spell than to say. What he said, he figured out something ingenious. He figured out this. If you've got a wave coming in with these wave fronts, remember these wave fronts are like peaks, and in between them are the troughs or the valleys. If you've got a wave front coming in, propagating this way, you could say, yeah, that wave front moves from here to there. That's what it does. Or he realized with a wave, you could treat every point on this wave as a source of another wave that spreads out spherically, if in the forwards direction. This wave spreads out spherically, this point here. He said that a wave front you can think of as an infinite source of waves. Each point is the source of another wave, and you're thinking, this is horribly complicated. What? What kind of mess is this going to give you? Well, if you add this up, these are going to interfere with each other, constructive, destructive, in a way that just gives you this same wave front right back. This is crazy, but true. If you let every point on this wave be another wave source, it will just add up to another wave front here. You'll just get the same thing back. And this is the key to understanding why diffraction happens, is because the wave was already diffracting, so to speak. It was already doing diffraction. Every point on here was doing diffraction. It's just it always added up with the other waves around it at every other point and gave you the same wave back. But when there's a barrier, when there's something in the way, these here can't rejoin up with their buddies. You just get this one here spreading out, and then this one down here spreads out. All the rest of these get blocked. Now that these are blocked, they're not going to get to interfere constructively and destructively with these points here. And so what do you see when it hits the hole? You just see this thing spreading out. So it was always diffracting, so to speak. We just didn't notice it because it always added up. When you've got a hole or a barrier, that's when we actually notice it. And this is the key to single slit interference, because if I get rid of all of that, if we imagine our wave coming in here like this, well, this wave's going to hit here. Every point is the source of another wave, so this point's going to start spreading out. This point's going to start spreading out. When we have a single slit, we really have infinitely many sources of waves here. And since some of them are blocked, we could see an interference pattern over here on the wall because these can interact and interfere with each other. What interference pattern are we going to see? Well, on the wall over here, we see a big old bright spot right in the middle. And if I were guessing, I would have thought that was it. Big old bright spot, because you shine a light through a small hole, single hole, you'll get a big bright spot there. The weird thing is, this jumps back up, goes to a minimum, a 0 point, and then it jumps back up, and then it comes back up again, and you get this. These are going to be not very pronounced. These aren't very pronounced. You get a big bright spot in the middle. These are relatively weak compared to other interference patterns that we've looked at. And down here, jumps up a little bit again over and over here. So this is the pattern you see. How can we get this? How do we analyze it? That's what we're going to try to figure out. To figure that out, okay, well, this is I said there's infinitely many sources here with when this wave gets to here. That would take a long time to draw. I'm going to draw 8. So let's say there's 1, 2, 8 sources. Let's just imagine there's 8 here to make this a little bit easier to think about. And the weird part is that this jumps back up here. So let's look at this minimum right here. Let's look at this point where it goes to 0, this destructive point. So the wave from this topmost point, this wave from the topmost, uppermost point has to travel a certain distance to get there. I'm going to also look at the 5th one down, this one that's basically halfway. How about these two? If these two interfere destructively, the argument I'm going to make is if these two interfere destructively, all the rest of them are going to have to interfere destructively. Why? Well, we know how to play this game. Let's draw our right angle line here. There we go. And so we know that, okay, if these are going to interfere destructively, this is the extra path length. This extra path length that this second wave, this lower middle wave, has to travel has to be what? If I want destructive over here, it's got to be a half wavelength, 3/2 wavelength, 5/2 wavelength. That's how much it's got to be in order to be destructive. So if this is the first point, let's just say that's 1/2 of a wavelength. And what's the relationship between the angle that this is at on the wall compared to the center line? Well, we already figured that out. Remember, that relationship was d sine theta equals the path length difference between these. That we derived. The screen had to be very far away compared to the width of the hole. But that relationship still applies. What would d be in this case? Now we have to be pretty careful. We have to be careful because this hole has a certain width. We'll call that width w. So if this hole has a certain width w, how far apart are these? These are not w apart. These are w over 2 apart. And so what's the relationship here for the path length difference between these two? Well, if they're w over 2 apart, I'd have d sine theta as the path length difference. So d would be w over 2 times sine of the angle that this makes to this point on the wall. And if their path length difference is lambda over 2, then that would be destructive. So equals lambda over 2. And this is a little weird already because look, I can cancel off the 2's. And what do I get? I get that w, the width of the entire width of the slit, times sine of theta equals lambda. This is giving me destructive. Remember, before, all the points that were integer wavelengths were giving me constructive. This time it's giving me a destructive point over here. And the reason is we played this game where w is the whole width. These are only w over 2 apart. That 2 cancels with that 2. Okay, but I haven't really proved that that they should all be destructive yet. This is just for these two. We've got infinitely many more in here. How are we ever going to show that if these two cancel, the rest of them cancel? Well, we'll just pair them off. Look at this. Now imagine you come down 1. I go to this one. I consider this wave that makes it over to here. And the next wave down from this other one here. So I move this one down a smidgen, I move this one down a smidgen, and I imagine these two waves traveling a certain distance to get over to this point. What relationship holds between these two? I can do the same thing. These are also w over 2 apart. So this here is also w over 2. So I'd get the same relationship. I'd get w over 2 sine of, is that going to be the same angle? Yeah, it's the same angle, same point on the wall. And this is really far away, so these approximations are whole where these lines are supposed to be approximately parallel because this screen or this wall's very far away compared to the width. That equals, well, that's going to be the same thing. I got w over 2 times sine of the same angle. Shoot, that's got to equal the same thing that it did up here. If the angle's the same, my w over 2 is the same, that's also going to equal half a wavelength. That's also going to be destructive. These two will also interfere destructively, and I can keep playing this game. I can pick this point here over to here and the next one down. These two would have to be destructive. I can pair them off and keep pairing them off. I'd get destructive for all of them. I could annihilate all of them by pairing them off and finding a partner that's destructive to that one. And so this really is a destructive point. This point over here, all the light is gone, completely annihilated, gives you destructive. So the short of it is that this relationship here, this relationship that w, this slit width, times sine of theta, the angle, same angle we've always been defining it as, equals integer wavelengths. This time, got to be careful though, this time this gives you destructive points.